Okay, so this is a talk which concentrates entirely on experiments with stable beams, which are important for the understanding of stellar burning. And I will try to explain that on different examples taken from primordial stars, nuclear synthesis, a recent topic again, solar neutrino measurements, then late stellar evolution, and then a topic which will be discussed later in the session, black holes, mass gap, and then sources and seeds for subsequent nucleosynthesis events. And finally, I will get back what Artemis has introduced in her first talk to the topic of novae. So the experimental opportunities to study these are related to deep underground accelerators, to inverse reaction techniques, and to an increasing amount to complementary measurements using Trojan Horse approaches or transfer reactions or things like that. Okay, nuclear astrophysics is the physics of nuclear processes in our universe. So it's as much nuclear physics as astrophysics, which provides the subsequent modeling on the impact of this, what we study. So when we talk about stars, that means long-term burning events with enormous timescales, which are typically determined by the Coulomb barrier between the critical reactions in the burning environment. So these reactions determine the chemical evolution of the stars, set basically the seed material for the subsequent burning stage. It determines the time scale, and and basically identifies the entire sequence of stellar evolution. This is controlled by key reactions. So that's different from explosive burning environment where you have an entire flow of reactions. Here in stellar burning, you have critical key reactions which need to be studied with large care and detail to a desired accuracy of 10%. And that's why we always look for the same reactions over and over again and try to make improvements in this. In a background-free environment, mainly because natural background handicaps the experiments. That's why we go underground or use inverse kinematics techniques. This is different from explosive burning, where you have an entire flow of reactions and where you basically have to look at collective nuclear parameters like masses, lifetimes, decay properties, and things like that for the R process to simulate the entire process. So explosive processes far off stability. That's why we need the radioactive beam facilities. And that is one of the main topics of this conference. But I will concentrate on the stable beam environments. Here is a summary of the experimental techniques which we use presently in the United States. First, on the left-hand side, the Caspar underground accelerator at SURF in Homestake Mine. It's an old accelerator. We constantly repair it, and that's one of our great handicaps. But it provides so far very useful information. This is complemented by the LENA facility. That's an above-ground facility built by Archampagne at a tunnel at the LENA laboratory, high-intensity ECR source, and I'm sure Art will talk more about that. And then finally, in terms of inverse kinematics, we have the St. George facility at Notre Dame, where we do inverse kinematics experiment mainly for the understanding of alpha capture reactions in stellar helium burning. Internationally, this is mirrored by efforts also underground, primarily, of course, the lunar accelerator in Gran Sasso, which is now upgraded by, I believe, 3 MV machine, which you see in the picture here. And that is now complemented just recently by the JINA accelerator, the 400 keV machine in the Jinping underground laboratory in China. It's a huge underground hall, and here you see basically a recent photo of the status of that machine. They have already measured one reaction, so they are trying to get into the game. In terms of recoil separators, one of the first one is a Dragon, initially built for radioactive beam experiments, but it's now more and more used also for stable beam experiments in inverse kinematics. And in Italy at Caserta, the IReNA facility, which is also used for stable beam inverse kinematic experiments. So that is basically the main tools. There are many more, but that are the main tools for the field. The critical question is that we are operating well below the Coulomb barrier, and here on the left-hand side, you see the classical picture of Klaus Rolfs, the cross-section exponentially dropping, and eventually we run out of steam, and it cannot be measured because of the natural background conditions in the background. And from there, the community usually has to extrapolate the S-factor data, that's a translation of the cross-section, the S-factor data into the stellar energy range. That is not as easy as shown here by a straight line, because at these threshold conditions, the cross-section can be influenced by a number of effects: the impact of sub-threshold resonances, single yet unknown resonances, and the sort of low energy tail of higher energy reaction contribution. So all of that has to be understood, and that requires a thorough simulation of the reaction cross-section. Otherwise, we might misinterpret it. I have a number of problems here where I want to demonstrate this, and I start with an example from early star nucleosynthesis. Most of you will remember here the spectrum or the abundance distribution in the Keller star, which one of the earliest star, which is characterized by high CNO abundances and also abundances of mass 40. So the question is, that a second generation star, presumably, how did you manage to transfer from primordial abundance distribution, hydrogen, helium, and a little bit of lithium towards CNO range? And the idea, the traditional idea, is that that is facilitated by the triple alpha process when the primordial star gradually contracts, but there are other alternative routes, and they are going through the cluster structure of lithium-6, boron-10, nitrogen-14, or lithium-7, boron-11, nitrogen-15 nuclei, which are characterized, whose alpha capture reactions are characterized by pronounced near threshold cluster configurations. And you see that here shown, and that is a result from Caspar experiments on the, for example, the boron-10 alpha N reaction, the boron-10 alpha P, and alpha D reactions. And all of this show an increasing tail towards low energies in the S factor, which signalize the pronounced alpha cluster, a state which was not known so far, and enhances the reaction rate by several orders of magnitude. If you take that into the calculations, and that was done by Andrea Clarkson and Pavel Denisenkov, you see basically a continuous flow from the helium-lithium range into the CNO range, which facilitates the build-up of the CNO cycles parallel to the triple alpha process. The triple alpha process kicks in later. The whole model is handicapped by proton capture reactions, because P alpha reaction can do a fair amount of back processing of the material, for example, boron-10 P alpha and so on, and that handicaps the process. And this depends entirely on the convective dynamic environment in first star simulations. Another example in that context is the origin of carbon-14. You saw in the Keller picture that there was a fair amount of, not carbon, calcium-40, was a fair amount of calcium-40. And Andrea Clarkson and Falk Herwig proposed that was sort of facilitated by a breakout from the CNO cycle via the fluorine-19 P gamma reactions. Now, we always thought the fluorine-19 P gamma reaction is very well known. And on the left-hand side, you see the P alpha gamma reaction, which causes a back processing into the CNO cycle, and the P gamma reaction measured by Aaron Couture, which basically leaks into the neon sodium cycle. Obviously, there are no measurements at very low energies in the underground environment, so that's something which needs to be done. But when you take on the basis of the existing data and perform an R matrix simulation, which you see here in the middle, then you see that the P gamma reaction is about 4 orders of magnitude weaker than the P alpha reaction, which is explained by the fact that the P alpha reaction is based on the strong interaction and the P gamma on the electromagnetic interaction. So we need to have a better understanding. This is all simulation towards lower energies. We need to have a better understanding, and that would be should be some of the future experiment for an underground experiment. Because in this present reaction rate version, the feeding of calcium-40 is not sufficient. Recently, there are interesting new results from the Borax-CNO detector. Here you see basically the neutrino or the spectrum from the Borax-CNO detector. And for the first time, they could basically determine the neutrino flux from the CNO neutrinos, namely from the O15 beta decay neutrinos. And you see that here in the lower picture. And that neutrino flux is pretty much determined by the N14 P gamma reaction. So the N14 P gamma reaction, which is the slowest reaction of the CNO cycle, is still pretty unknown in the low energy range because of, despite the fact that there has been extensive measurements of the lunar collaboration and the LENA collaboration in red, the lunar is in yellow. And there is some uncertainty in the extrapolation, and in the upper picture, the distribution of R matrix fits reflects the uncertainty due to the contribution of the subthreshold resonance in O15, which has been recently measured. The lifetime of the state has been recently measured, and the width of this fit distribution reflects the uncertainty in the lifetime. So it did not provide clarifying information. But however, when we take into account a broader range of R matrix data, then you can see basically that the lower energy data are within the given uncertainty range. That seems to be a little bit in disagreement with the Borax-CNO data, because the Borax-CNO data seem to indicate, at least according to Frank Kellerpreis, that the neutrino flux from O15 should be a little bit higher. However, the figure I show here is not the full picture. There are some inconsistencies still in the data which need to be explored, and that is when you do an R matrix fit over the entire ground state transition of nitrogen 14 P gamma, you see severe disagreement in the higher energy range, which were obtained for the benefit of the low energy data. However, if we improve the fit, if we try to fit the high energy range better, then we would expect higher S factor at the lower energy range. So there's still some inconsistency, and we are presently trying to look into that by additional measurements to resolve that issue. Carbon-12 alpha gamma, presumably Willy Fowler said that's the Holy Grail of nuclear astrophysics. I never found that quote, but nevertheless, it's of extreme interest. It impacts the late stellar evolution towards type 2 supernova. It defines the white dwarf composition and ignition conditions in type 1a supernova. And as we recently learned from a Bob Farmer paper, that it defines the trigger conditions for pair instability supernova. I will not talk more about it. He will give the next talk and discuss that in more detail. On the left-hand lower side, you see the present uncertainty in the range. It ranges between 15 and 20%, and that is mainly based on an R matrix extrapolation of all available reaction data feeding the O16 compound nucleus. 15%, according to the modelers, is still not sufficient. They want 10%, so the challenge remains, and a number of new initiatives are in preparation. I'm sure Lunar MV, with the new accelerator, will try to measure this reaction with improved background subtractions at Gran Sasso. Then I'm also pretty convinced that Art Champagne with Lena, I called it Lena MV here for the talk, will try to do another round on this reaction. And then, of course, there's a number of studies based on inverse kinematic measurements that was pioneered by the Dragon group at Triumph. However, there are other experimental approaches, mainly using inverse techniques, taking advantage of the higher cross-section in the O16 gamma alpha rather than the carbon-12 alpha gamma reaction. There are three different groups. First, in Coulomb dissociation at GSI and Frankfurt, that's Kirsten Goebel and René Reifert. They're trying to measure that. I think first tests have been done. Then the MESA group in Mainz tries to do it by electron dissociation. There's a new proposal. On the right-hand side, you see basically what they claim to be able to do in the future. That's all proposal. You see basically in the first round, they go down into that's mainly comparison to existing data. And in the second round, they really will push down into the gamma range. And then finally, photon dissociation that was proposed, and first test experiments were done at Higgs at Tunnel by Moshe Guy and collaborators. And that initiative has moved now to Eli, the new facility in Romania, which is still in the construction phase. Neutron sources. Neutron sources is extremely interested for the understanding of the S, the I, and the N process, which takes place in RGB, red giant stars, asymptotic giant branch stars, and in early stars, and also for the N process in the supernova shock front. So the neutron flux is determined again by the Coulomb barrier, because it depends on alpha N reactions, which act as the neutron sources. And in some cases, these alpha N reactions are endothermic, so they have to compete with exothermic alpha gamma reactions, which may eat away a whole bunch of the seed material. So one of the important sources is the carbon-13 alpha N reaction. There has been a recent very successful lunar experiments by Andreas Best and collaborators. And I don't have the data. The data are not published. But what I have is here an R matrix simulation of all the reaction data, which was recently done by the Notre Dame Oak Ridge collaboration. And see, the predictions are that the S factor is slightly below the previous claimed reaction data, which we had to fight with large underground background processes. And I understand that the lunar data seem to confirm that. The critical issue is contributions from higher energy resonances and interference effects. And here basically see a whole bunch of reactions at higher energy of this, measurements at higher energy of this reaction. And you see R matrix simulations, which basically feed down here and explain this extrapolation. The second reaction is the neon 22 alpha N reaction. Last measurements, successful measurements, were done about 20 years ago by Jägerdahl in Stuttgart, and they found basically the strong resonance here at 830 keV, which is also mirrored by a strong resonance in the competing neon 22 alpha gamma channel. This reaction alpha N has a negative Q value, so it kicks in only at high energies, at higher temperatures. So at lower temperatures, neon 22 alpha gamma is already burning through a number of potential resonances which have been identified by indirect reaction study, and that is an R matrix prediction that may or may not have anything to do with reality. These reactions need to be measured, and presently, actually this week, there's an attempt at CASPA to measure the alpha gamma resonances, and next year there will be also an attempt towards the alpha N reactions, and I'm sure similar experiments will be done at LUNA and at LENA. Carbon-12 fusion. This is a reaction which triggered recently a lot of interest. And on the left-hand side, you basically see the world supply of data of carbon-12 alpha gamma with a fit, which is pretty much complementary to the fit of Coughlin and Fowler 1988. But about 10 years ago, a new proposal was made by the Argonne group that we should expect something like a hindrance in the fusion of two heavy nuclei, and that would basically, in the extreme, convert the S factor to something like that. And obviously, there's a couple of orders magnitude difference in the subsequent reaction rate.
So, Michael, you do need to move the process along here because the time is
faster.
coming up.
On the right-hand side, there's a recent Trojan Horse experiment which claims a number of subthreshold resonances at that one. And you see basically here the prediction of the Trojan Horse result, and that disagrees with recent measurements done at Notre Dame. If you convert these results, correct for Coulomb barrier, Coulomb wave functions effect from, as supposed by Akram Mukhamaedzanov, you basically get the two lower curves, in particular the green curves, if you match it to the Notre Dame band. There's a lot of uncertainty. And my last point is nova explosions at higher masses. The nova reaction flow goes towards the line of stability. So there are a number of stable nuclear reactions have to be measured. First measurements have been done by Christian Eliades several years ago in the chlorine and argon range, but we need more measurements to see if that reaction path goes beyond the calcium range. And with that, I conclude and leave it up then. Just leave it up there and ready for questions.